Hi folks, the last little while we've been talking a lot about the convergence of a series, in particular whether a series converges or not. We haven't really spoken much about what it converges to. So far we can only determine that if the series is a convergent geometric series, or if we can relate it to the Taylor or Maclaurin series of a known function. We're going to take a look at an example here where we actually can determine the convergence of a series and what it converges to. Okay, but it's a special type of example. So these types of series are what we call telescoping series. Okay, we'll see in a little bit why they take on that name. So let's take a look at one example. Okay, a simpler one here, and if we take the sum I going from 1 to infinity of 1 over I minus 1 over I plus 1. Okay. Now, if we take a look at the first few terms of this series, we see that, well, we have 1 over 1 minus 1 half. And then for I equals 2, we have plus 1 half minus 1 third. And then we have plus 1 third minus 1 quarter, and so on and so forth. So it looks as though all the terms subsequent to the first one seem to cancel each other out. Now, we can't sort of make that assumption. If we want to determine the exact value, we really need to go back to the definition of the sum of the series. And we recall that the way we defined the sum of the series was the limit of the partial sums. Okay, so let's take a look at that here. If we look at S1, okay, well, we have just 1 minus 1 half. And then we look at S2, and we've got 1 minus 1 half plus 1 half minus 1 third. Okay, here the 1 halves, and we can say this is equal to 1 minus a third. And then let's go one more. We go to S3, we have 1 minus a half plus a half minus a third plus a third, and then minus 1 quarter. And again, we've got all these middle terms cancel out. We're always left with the first and last term. So we have left with 1 minus 1 quarter. So now that we see the pattern, we can say that Sn will be equal to 1 minus 1 over n plus 1. Okay, and now if we take the limit as n goes to infinity of Sn, we end up with the limit as n goes to infinity of 1 minus 1 over n plus 1. And of course, that second term approaches 0, so our limit is just equal to 1. Exactly what we had anticipated. Okay, so we'll take a look now at another way in which these types of examples can be given. Okay, so I'll just go to a second sheet here, and we're going to take a look at this example here. So we'll take the sum, and just to change things up, I'll use n this time. N equals 1 to infinity of 1 over 2n minus 1 times 2n plus 1. Okay. Now, if we think of what we did before, if we think of the first few terms, we'd have, well, 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7. That doesn't seem to quite give us what we had in the previous scenario. So what we're going to do is we're going to take this expression and use an old trick. Okay, we'd like to rewrite it as two separate terms. Okay, so we saw that before. We're going to write it as partial fractions. So our first goal here is to rewrite this expression, 2n plus 1, as two separate expressions. And so here we know that we're going to write a over 2n minus 1 plus b over 2n plus 1. This is what we'd like to have, and we can add everything up to get a times 2n plus 1 plus b times 2n minus 1 all over, well, 2n minus 1, 2n plus 1. Okay, and we've seen this before, and the trick that we saw to solving these fairly easily is to choose a convenient value for n. Now, you might sort of say, well, n can technically only be an integer. Okay, but remember, all we're trying to do is to solve this equation, to determine what a and b are. So I'm going to allow myself to choose any value for m. In particular, as we remember, we want to choose values that are going to make each of these brackets equal to 0. So if I pick, in this case here, let's say I pick n would have to be -1/2. Okay, so I can rewrite the equation 1 equals, well, -1/2 will make this first term equal to 0. And so we've got b times, well, -1/2 times 2 is -1 minus 1, -2. So b is just equal to -1/2. And then we can do something similar for this bracket here. Here we'll take n equals +1/2. So we end up with 1 equals a times, or 2 times 1/2 is 1 plus 1 is 2. And so a is equal to 1/2. Okay, so again, since we were just trying to solve this equation, we allowed n to be whatever value was useful for solving the equation. So that means that we can now rewrite this series as n equals 1 to infinity of 1/2 over 2n minus 1 minus 1/2 over 2n plus 1. Okay? And this is where we're starting to see the pattern. What should we be looking for the type of series that we call a telescoping series? Okay? We need to see scenarios where the same terms will pop up when we look at subsequent n values. Okay. Now I'm going to go against my own rule here and reuse n for a general term, which we'll see in a second. But let's start with S1. So we have S1 here, and we realize that again we're going to have 1 and 3 in the denominator. So we're going to have 1/2 over 1, so 1/2 minus 1/2 times 3. So 1 times 2 times 3. Sorry, 1 over 2 times 3. And then we take a look at S2, and we got again 1/2 minus 1 over 2 times 3. And let's take a look at what's going to happen here. We're going to have now, instead of 1 and 3, we're going to have 3 and 5. So plus 1 over 2 times 3 minus 1 over 2 times 5. And we're starting to see the same pattern. The middle terms are canceling out. So let's do one more just to make sure the pattern continues. So 1/2 minus 1 over 2 times 3, and plus 1 over 2 times 3 minus 1 over 2 times 5, and then plus 1 over 2 times 5 minus 1 over 2 times 7. And again, we see all the middle terms cancel out. So what we're left with in the end is Sn equals, okay, 1/2 all the time, and then minus whatever the last term would be. So minus 1 over 2 times, well, if we compare here, we just have 2n plus 1. Okay? And now that we have a formula for Sn, we can take the limit to determine the sum of the series. So limit of Sn is the limit as n goes to infinity of 1/2 minus 1 over 2 times 2n plus 1, and as before, that term approaches 0, and so we're left with 1/2. So why do we call it a telescoping series? Well, they want you to think of those old-fashioned telescopes where you've got all these small bits will sort of collapse back into the first larger bit. Okay, in the same way here, everything else collapses down to this first term. Now, just to give you a little heads up, be careful. Depending on how the expression is given, it might not necessarily converge to the first term. So I'll just give you a little warning there. You really should go through the process of seeing how things cancel out in your partial sums. So what I'm going to suggest is that you work on section 9.4, number 50 and 53, and those are a couple of nice examples to practice telescoping series.